Alright guys, well, feast your eyes on this. We're going to be talking about telescopes now. So, keep in mind, you guys are going to want to try to be able to answer the questions at the end of this presentation. So if you want to skip ahead and look to those questions right off the bat, you kind of might have a focused guide of what type of notes you should be taking. Okay, so let's start. Where did telescopes begin? So we're going to go ahead and start with Galileo. So actually, Galileo improved upon a sight glass by Leeuwenhoek around the same era, which was used to look at much smaller things, and he just kind of adapted it to look at things that are big and far away. Okay. So he invented the first telescope in 1609. He discovered the craters of the moon, the rings of Saturn, which he thought, and many people at the time thought, looked like ears. Okay. Jupiter's 4 largest moons and sunspots. His discoveries proved that the Copernican system, disproving the geocentric model. So remember, Copernican is talking about the heliocentric or the sun-centered model. Okay. And by the way, here's a picture of his telescope. Okay, this is how it worked. Okay, so the starlight comes into a lens, which focuses it into a. So this is a converging lens, which makes the light bend towards something. This actually is a refracting lens, or a diffusing lens. And this part here, the thick part of it, it would actually cause it to go up a little bit and then back down this way. This is what spreads the light a little bit and makes it focus further away. These are just conveniently positioned so that they focus on whatever the eye is supposed to be looking at. Okay, now we're going to look at Newton, 1668. Newton developed a telescope in 1668. The telescope replaced the lens with a mirror to reduce chromatic aberration. So chromatic aberration means that since the medium of air, which we talked about when we watched the Cosmos video, so we got white light coming in. When that white light hits a new boundary right here, the white light, of course, is comprised of all the colors of the rainbow. And those colors of the rainbow, as we know from earlier in the chapter, are different frequencies, right? So the violet colors are going to be the shortest wavelength, followed by like the blues, and then eventually we get to the reds, right, which are much longer wavelength. Well, you can see here that if this incident white light, which I'm going to go ahead and make gray right now just so you can see a little better, this incident white light hits the lens right here, you can see that which of these colors bent the most. Well, if the regular path was supposed to be a straight line, you can see that compared to the normal line, the violet and blue bent the most, and that's because the wavelength is really small and it most closely matches the size of the molecules in the glass, so it's going to interact with it and refract and bend more. Okay, so just by the very nature of the way that refraction works as you enter from one medium to another, you're going to get more bending for certain colors than others. So you're going to end up not having an image that focuses too well here. It's not very coherent. So you end up with a picture that looks kind of like that, okay, where it would be a building that looks like this. The chromatic aberration kind of makes different colors focus at different points. Okay. So Newton is credited for inventing the reflective telescope, and that's to fix the idea of the refractive problem in a lens. Okay, and William Herschel. William Herschel designed the first large telescope with a large reflector. Okay, the 40-foot telescope featured a 4-foot mirror. That's huge. What you need to know is the larger the mirror, the better the image, the more light it can collect. So this is more information, okay, more info. Just like if you had really, really big eyes, you'd be able to see much more of the night sky. The way around not having large eyes is just to look for longer and to allow the light to collect over a period of time. And certainly you've seen those pictures of the night sky where you might see something like this, where it's like the stars are kind of like going in circles like that in the night sky. And that's because that's a long exposure photograph that's being taken, so it allows light to be collected over a long period of time. Okay. Although the telescope is credited for discovering Uranus and observing very faint objects, it was rarely used. The Leviathan, 1845. The Leviathan of Parsonstown was the largest telescope until 1917. The 71-foot telescope featured a 6-foot mirror that weighed 3 tons. The telescope was used primarily to view the nebulae and star clusters. Spiral galaxies were documented but had not been identified during this time. Hey, Hooker, 1918. The Hooker telescope had a 100-foot mirror and consisted of 30 motors for rotation and movement. The mirror took 5 years to polish and build. So the more specular the image, the more the original object image would be preserved. It would be the largest telescope for the next 75 years. Using the Hooker telescope, Edwin Hubble discovered that the Andromeda Nebula existed outside of our Milky Way, and that's a pretty astounding discovery. At the time, we didn't know if there was anything beyond that. He also discovered that the universe is expanding, and we start getting into this thing called the Hubble constant, which is the expansion rate of the universe. It was his life's long work, and it was the impetus for a lot of his want to keep observing the universe and kind of look at the shape and the cosmic evolution and what the ultimate fate of our universe would appear to be. Okay, now Hubble, 1990. You saw a video on this yesterday. Launched in 1990, the Hubble telescope would view distant objects in visible, UV, and infrared spectra, keeping in mind that, remember, the electromagnetic spectrum is comprised of a continuous spectrum of things that go from most energetic to least energetic. We got the gamma rays, we have X-rays, ultraviolet, then we have visible light, UV, then we have infrared, microwave, and radio wave. So this is the order of the electromagnetic spectrum. In fact, I'm going to go ahead and make this violent just so it's a little easier to see. Okay, so make sure you understand the order of that, and know that by 1990 we started really wanting to look at the universe in spectra besides just visible light. In the 60s, we started playing around with X-rays and looking at the sun and X-ray radiation, putting telescopes outside. We wanted to put telescopes outside of the atmosphere so we could see what sort of radiation was coming from different objects. Okay, so I want you to take note of this. The Hubble telescope, the space telescope, only has a 7.9-foot mirror, but it could still take very detailed images without interference from the Earth's atmosphere. We talked about this a little bit in class today. Remember that when you go from one medium to another, so right here, you've got the medium of nothing really, or vacuum. And as you go into the Earth's atmosphere, you hit a new boundary, right? You hit a boundary that all of a sudden you're hitting atmosphere and you're going to get refraction, right? And depending on the type of light, depending on the color, you might get lots of scattering, you might get very little bit of scattering, right? So because you're in outer space, you don't really have that change of medium. So you don't necessarily need a larger mirror to be able to see things in fine detail. Okay. Notice here, though, that the physics, the ray diagram of the physics is largely the same, right? You have incoming light that's incident upon a mirror, secondary mirror that focuses it on a focal point, which a computer or a photon collector can put into like some sort of monitor and transmit back to Earth. But I mean, the first 2 to 3 steps of how this telescope works is the exact same as it was 300 years ago. Here's some images that the Hubble telescope was able to see. Awesome. Okay, Spitzer in 2003. Spitzer was launched with the mission to view stars using infrared technology. It has been able to pierce through thick gas clouds and nebula, and that's because we're using things that actually do not interact with dust. Okay, so let's pretend this right here is dust. Well, if I'm using something that has a really small wavelength, well, it's going to crash into every little small particle there. But since we're using infrared's much longer, it's going to pass straight through. So actually, if we look at most of the universe in infrared, we can actually look straight through a lot of the arms and tendrils of dust that the Milky Way has. Though the main objective of Spitzer has passed, it is able to detect stellar nurseries, centers of galaxies, and failed stars and exoplanets. And again, that's because radio waves are transparent, or dust is transparent to radio waves. Radio waves and infrared. Anything that's a long wave. Okay, Kepler in 2009. The Kepler telescope's purpose is to locate exoplanets that would resemble Earth. As of August 2018, it has found 2,300 27 confirmed planets with 2,244 candidates, 30 Earth type in the habitable zone. And what is a habitable zone? Okay, so the habitable zone is a range of distances that exists. So if I say this is my star right here, the habitable zone might be some radius in which, if I were to inhabit, that planet just might have a chance of surviving in that zone. It's got just enough light and nutrients that it can get from the sun, so energy that it can get from the sun within these zones, right? Now, there are other factors that matter too, like, is there another star present? Are there other large planets nearby that kind of gravitationally pulling inward and kind of messing with it and causing a lot like really bad tidal forces? But all things held constant, we just don't worry about that. The habitable zone for a given star is just the range in which you can place a planet and it have lifelike qualities, like the amount of energy that it receives. Okay, of these planets, so these some odd 2,244, 30 are strong candidates for the possibility of life due to their location and composition. And if you watch the show Raised by Wolves, I think they're on Kepler 244b or something like that, or 44b, which is where they're at. It's a pretty interesting show. Okay, TESS 2018. Launched in April of 2018, the mission will find exoplanets that periodically block part of the light from their host stars. Events called transits. So this is also called, just very generally, an occlusion. So if something occludes something else, it means it gets in front and blocks it. It's actually how we kind of discovered Neptune, right? We let, I think it was the sun or one of the moons of another planet pass in front of it, and we saw that it was blocked out a certain number of times, so we knew that there were rings. Okay. TESS will survey 200,000 of the brightest stars near the sun to search for transiting exoplanets. James Webb 2021. This is a really interesting telescope, or an observational device. The JWST is set to launch on October 31st, 2021. That's like my birthday. It's really cool. Happy birthday to me. It is designed to extend the discoveries of Hubble by having greater wavelength coverage and higher sensitivity. So what does that mean by greater wavelength coverage? Remember that the Hubble telescope looked at infrared, it looked in visible light, and what was the other one? Is it X-ray? I don't think so. It might have been microwave. We'll check that again. So if it has a greater wavelength coverage, that means it's going to be able to look outside of those. So the more wavelengths and types of electromagnetic spectrum you're able to look at, the more objects you're going to be able to observe. You're going to be able to observe highly energetic objects. You're going to be able to observe things that are cooler, right? That might not give off visible light, but nonetheless give off things like radio waves if they spin and have magnetic fields. The JWST will be able to look closer to the beginning of time and the first galaxies. It will be able to see through dust clouds where stars and planets are forming today. Those are like the stellar nurseries. Okay, and remember when we're talking about looking back in time, it's not that we are time traveling. Okay, it's not time travel, but we are looking into the past because light has a finite speed, very, very fast, but nonetheless finite. So let's say I'm an observer here on Earth. Okay, I'm going to make us a red man, whatever. You can also have green people. Sure, why not? Okay, so here we go. So let's say we got incident white light coming from the very edge of the universe. Well, if I happen to put a telescope in space, it's going to have gold wings. It's a terrible telescope. And I'm able to see all the way back. As the further I look back, what happens here is this light takes time to travel. So the closest image are going to be the newest. The furthest back I look is going to be the oldest. So the further out I look into space, the further back in time I can see. This lets us look and see like what the universe properties were back in the day, and kind kind of how the universe used to behave, and it gives us an idea of the trajectory. It's part of the evidence of the Big Bang that we know we all came from a single point at some point. Okay, here's the schematics of the James Webb Space Telescope. Okay, and here's a comparison of the Hubble mirror. Look at how much bigger this array of mirrors is. These hexagonal reflecting mirrors right here go straight into that collector. Okay, here is a comparison of how far out the space probes are going to be able to see. So these are ground observatories in the 90s. Notice they're limited, even though they're huge, they're limited compared to some of these other space telescopes because of the Earth's atmosphere. Hubble Deep Field, which did some amazing observations of just kind of arbitrary pieces of space that showed us that there was things way beyond what we thought were even there. And then we have the Hubble Deep Field, the Hubble Ultra Deep Field infrared, so looking at infrared. And then in the future, we'll have the James Webb Space Telescope, which can look 200 million years, greater than 200 million years in the past. The Giant Magellan in 2022. So this is coming up. It's definitely going to happen, I think, right? 2020 can't last forever. The Giant Magellan is a ground-based telescope set to see its first light in 2022. Because of its enormous size, it will be able to see the cosmos in advanced clarity and sensitivity. It is designed to view the formation of the first stars, explore the origins of the elements, and find the causes of dark matter and dark energy. So if any of y'all who are familiar with dark energy and dark matter, what do you think they are, right? So from what I understand, let's say this is our universe right here. We're kind of like in this bag, right? And we have all the little stars and all like the galaxies and things like that. But there's no reason to believe that, you know, we originated from this single point and expanded into this space on this surface here. Who's to say that this is just kind of like a local expansion, and that there were actually, from this point, maybe there was an expansion this way, and we just kind of it's so far out that we can't really observe what's happening out here, right? So even though we can't observe it, it doesn't mean there isn't stuff there. And as far as we know, there isn't really a limitation of how far away gravitational pulls can have on us. So this unseen matter could actually be pulling on our universe, right? And it could be the cause for accelerated expansion, even though there doesn't seem to be something there. Now picture this. Maybe there are even more of these little bubbles that are around us all over the place. This is one of the hypotheses posited by scientists of what possibly dark matter and dark energy could come from. These different bubble universes that surround us, that all expanded simultaneously from the beginning, or maybe we're already there, that we just can't really see, but nonetheless have an effect on us. And we know that there has to be some reason that the universe is expanding in spite of what the laws of physics should tell us. Okay, here's the building of the Giant Magellan. And star shade in the 2020s. So if you ever try to look at something at night, you notice you have a lot of light pollution if you live in San Antonio. So you go out to the countryside, you can see really well, right? Well, if you just get rid of all that pesky light, if you had a way to block it, all of a sudden you can see really well. And certainly if you've ever had your cell phone up to your face while you're outside, you look up and what do you see? It's just pitch black, right? So you need a way to block that light. Well, star shade in the 2020s is going to do just that. It's a flower-shaped disc designed to block out starlight from a distant star. This flower shape bends light more to darken the star and make exoplanets more visible. The star shade will work with most telescopes of the future to enhance images of exosolar systems. You can just kind of place this in front of them and kind of align these with some nice timing, right? If you know the rotational period of like a telescope, you know the rotational period of the star shade, you can actually get some of this light to filter out and bend away, and then you can look at these other things much more clearly. Okay, LUVOIR, 2030s to 2040. So this is hopefully something that happens within our lifetimes, right? It's a large ultraviolet optical infrared telescope. It's NASA's strategic mission concept study for the next generation of UV OIR space observatory. So it has a lot of the same. So look at this right here. So here was the Hubble, here was the James Webb, and now look, here's LUVOIR. Look at how how many mirrors are part of that. A lot of these things like to use gold because does really well in space, and also it can be bent down. It can be smashed down into really, really thin plates. And it can also be used as solar cells too, potentially. Okay. Here's some of the components of it. Here's the concept for it. Okay, so review questions. Who invented the first telescope? Know that Newton is credited for inventing the first blank telescope. What type of aberration did Newton reduce with his telescope? Which telescope discovered Uranus? In which telescope did Edwin Hubble make his discoveries? What telescope was launched in 1990 that viewed the universe using the visible spectrum and has captured thousands of amazing images? So we saw a video on that today. What telescope has found over 1,200 exoplanets? What telescope will be launched in 2021 and be able to view farther than the Hubble? Okay, go ahead and make sure you get all these things down, get little pictures of everything, and then annotate them.